Hello, welcome back. My name is Andrew Lee. I teach at the Kyoto Institute of Technology. The title of my talk is really kind of technical looking, and so I feel a little bit of an obligation to try and connect it to cultural DNA. So before I get to all of the nitty-gritty stuff, I am just going to make a very fast run through what I think is the logical connection from cultural DNAs and how you can actually get to shape grammars, or actually specifically how do you get to an implementation of shape grammars. So with cultural DNA, there's a lot of things, of course, that you do, but one of the things you do is think about style. You look at cultural artifacts and you try and understand them. And this happens to fit very well with a description of the problem by Steiny Mitchell at the end of their Palladian grammar paper in 1978. And it's very interesting because I think this paragraph actually is a very nice, very succinct, very precise description of the problem, and yet most people seem not to know about it. So I just pointed out, I'm not going to make you read it unless you've already read it right now. The translation, okay, in brief, what they wrote was about buildings, but I think we can generalize safely to any designed artifact. In general, they have an implicit definition of style as a set of similar designs. It's not, in other words, the question is not about the process so much, but just about the existence inside or outside of a set. And of course, the word similar here is also important, although they don't actually say what they mean by similar. Similar here is an appeal to your intuition. Now, given that, then your problem is, especially in cultural DNA, is that you have a finite number of things that you are looking at and you think they are similar, and therefore you want to understand them. What does it mean to understand them? Well, their proposal is that an operational definition of understanding involves being able to do three things, and these are the three things. One is you show how you can make another design in the style. Second is, given a design that you haven't seen before, can you show how you can test whether it is in the style or not? And the third thing is explain why they are similar. In other words, originally you started out with this group of designs that you thought was similar. You want an explanation. Why do I think they are similar? Okay, it's not just we now have to try and somehow externalize our intuition. Okay, now there are a number of places, if you read this really carefully, you will realize that there are quite a few things that they have glossed over, okay? But unfortunately, this is not the time to talk about it, even though it's actually really interesting. Now, what kind of tools can do these three things? Not a list, okay? A list lacks explanation. A list only tells you membership or not membership. Okay, so a list is no good. The answer, which they actually don't say, but seems to me obvious, they're pointing to a generative description. And a generative description can take many forms. The kind of most obvious one is a computer program. It's a formal description of a process which would then lead to a set of output. Or something like a production system such as an L system. Or, surprise, surprise, a shape grammar. Although they, were a little bit discreet and they didn't say that in the paper. But, okay, so a shape grammar can do these three things. And if you are new to shape grammar, you'll just have to take my word for this because we have to move on. Now, shape grammar can do those three things, and it has one more advantage, which is that it is visual. Okay, now if you're interested in design, you look at things. And you draw. And so this is where shape grammar is different from L systems, different from computer programs, and this is its big advantage, in theory at least. And I would also like to point out, I would like to thank one of my reviewers who pointed out that Grasshopper is also visual, so, you know, what's the big deal? And so I thought about this a little bit, and then I realized, well, okay, it's, grammar is visual in terms of semantics, the content of what it's doing. It's not just how the operations are connected. It's actually what the operations operate on, which are visually captured. Okay, now it's a very quick example. This, of course, is my dissertation, and you know, following incarnations. The Yingzhaofashe is a building manual from China, and okay, so here's our corpus. This is a very small part. Actually, in the book there's a set of 18 drawings like this, sections of buildings. This is just showing the sections of 6 rafter buildings. So 1, 2, 3, 4, 5, 6. In Chinese architecture, this is how they measure the depth of the buildings, the number of rafters. So for 6 rafter buildings, they show 5 sections. And there's also this description here, which is very interesting because it talks about the number of concrete elements. As architects, normally we would talk about the spaces. We would say there are 2 big bays, 2 small bays. But actually, these written descriptions don't talk about spaces at all. They talk about physical components. So this is something worth noticing. Anyhow, so here's our fixed corpus, okay? And we assume them to be similar because they're in this book, okay? Now, the grammar. This is a grammar that I wrote, and basically what it shows you is that you have these different rules, and you can install a second column, this is the front column, at a distance of 1 rafter, or a distance of 2 rafters, or a distance of 3 rafters. That's the basic idea. So this is a kind of generative hypothesis about how we can create these different sections. And the reason why it turned out like this is because this is also at the same time generating the description, the textual symbolic description that was on the side of those drawings. So this is all on paper, and I got a PhD for that. Now this is what the grammar predicts. Okay, we now have a new grammar, and it can produce sections like this. Now, these are predictions, and the question is, are they in or out? Okay, that's another question which I've written about, and we don't have time for it today. But anyhow, so that's what it does on paper, and I will show you an implementation that I did of this quite a number of years ago. Okay, so there's our 6 rafter building. This is a flash thing. Okay, here are all of our rules, and here's how you can alter this beginning shape, the initial shape. So we can add a column, a column in the front at a spacing of 1 rafter, and maybe you can, now you see the dark and the dimmed rules are the ones that show you which ones can and cannot be applied at any stage. So this is a kind of real-time interaction here. And so we can just do that, and then here, now, we just did all the interesting part. This is the boring part where it's just doing all of this housework down here, dealing with these labels. But that's part of the bargain. Okay, then we need to fill in all of the pieces of the roof structure. So we can do that automatically. And now this fills that all in, going from left to right. Then the last step is to clean up the label. This is the label, the description. Okay, there appear to be certain rules about how you actually express that. Okay, and there's our final thing. And now we'll just play back the entire process. Okay, now this implementation is a dedicated implementation. It only does this one grammar, and you cannot change this one grammar without rewriting it. So, at the time I thought I was actually really smart to do this, and that I would solve a lot of the problems of shape grammar. And then I did it, and of course it didn't work. So that was kind of an interesting thing to find out. This dedicated implementation is instructive as far as it goes, but it kind of then said, well, but I want to change it. You know, and there has to be an easier way. Okay, so where are we? What did we get? Okay, so my next project was to make a general interpreter. Now we're getting to software, okay? General interpreter has two parts. One is the interpreter proper, and the other one is the grammar editor. And the interpreter proper, I would like to give credit to 5 minutes left or 5 minutes used? Left. Okay.
4.5.
Okay. Okay, then I will just run straight to the demonstration, okay? Okay, let's see, where is it? Okay, oh, sorry, geez, let's see. Now I can remember where it is.
And then exciting enough that tomorrow you will, some of the students, you have a chance to really do practice with his interpreter. Okay. So tomorrow we have a Czech grammar workshop. Okay.
Sorry, I accidentally closed the window, so now I have to find it. Okay. You can keep on doing the publicity while I look. Okay, here we are. So, okay, so what we do is we have, okay, everyone recognize this. This is Grasshopper. Now we have a bunch of scripts, and they help us when we set up. We need to have an initial shape and an initial and a rule. So that's how we start. And these are 3D cubes you will see, and we draw the shape inside the frame. This I call it a frame. So we just made an initial shape. Now we're making the first rule. Each initial shape and each rule is on a different layer, and that's how the parser can distinguish the different elements. So this is a grammar that, now we're drawing in 2D, but the interpreter actually is 3D. And I think I do later a little tilting thing so you can see that it's actually 3D. One of the things that, when I started using this and started showing other people, there are a lot of kind of traps that people fall into. You have to make sure that you're actually on the right layer, and you have to make sure that all these things are aligned. So I exploded one of these rectangle things. Okay, so now what we're doing is naming, we're going to export this, what we're doing is we're making a second rule. So we just ran a script to create this second rule. It created a new layer with a rule of our choosing, a name of our choosing. At the time, I thought I was very fast. Okay, so this was not the right layer, okay? You have to go through and check. I made this checklist of things. So there's the 3D version. You can see that everything is actually in 3D, and all of these things are drawn on the XY plane. So now, okay, I think we're about to export the grammar. So now what will happen is we're creating a DAT file, a special file with a special format. It's basically text. And we give the file name, and it will suck out everything in the Rhino document and put it in this. standalone application, we have to now switch to that application. This is it, and we're just opening the file. So there's the rule, here's our current shape, and here are the two rules. This now shows us all of the shapes that can be gotten by applying either of these two rules under any transformation. So I'm just showing you all the different possible things. And this is just here so you know it's actually thinking, because sometimes it takes a long time and you really doubt whether anything is happening. So these are all the different versions you can choose. You can also go backwards if you don't like something. Try again. So now what's going to happen here is you'll see that we are going to detect this square, which is an emergent square. So this just to point out that it does handle emergence, not 100% of cases, but the cases in which there are involves significant points. It's impossible to do total emergence matching because a lot of things are infinitely many subshapes. So this is we just flip to 3D so you can see that it's actually a 3D thing. Now, what we're doing is we're saving the derivation from the first initial shape to the final shape is a derivation, and we're making a DRV file, and we're going to put it back into Rhino. So it's going to draw it right here. The whole derivation. And it'll include, it also shows the rule that you apply. Okay, so now we have this, and the great thing about this is that it's in Rhino. So now you can use this to publish your paper. You can use this to, you can turn it to a, well, okay, this is not a 3D one. Do I have time for, how much time? No? Time, okay. Then I won't show you the 3D one. But this now, the important thing is that this is in Rhino, and so believe me, you can also do this in 3D. So you can convert it to a surface model into a solid model. You can 3D print it, you can laser cut it, you can do anything. Okay, it's in the conventional work stream, which everyone knows and loves. You could even do something with Grasshopper. You could take this and you could transform it somehow. So that's what I've done. Okay, I'll just show you. Well, I have some kind of conclusion, but I guess we can stop here. So questions?
You have to attend tomorrow. Okay.
I'll ask you. Easy question. Are they all lines or are there also?
Oh,
Because you talked
oh,
about.
the other one has labeled points. Sorry. Yes, the other example that I don't
Yeah, but I
have.
mean, if you're talking about fabrication, etc., you
Yes.
have to convert it into surfaces or.
Yes. But it's in Rhino, so it can be done.
Exactly. Okay.
Are you selling this? Or are you put it on the website?
Are you buying? It's still under development. I don't think it's quite good enough for people to spend money on.
Are you gonna put your beta version on your website?
Oh, well, okay, yes, that's one of the things I was going to show you. It's on my website, so, okay, last thing, okay, what comes next? Okay, is get other people to use it. So that's you, and you can get right here, and I uploaded it this morning, sitting there. And I think everything should be up to date. So if you go to my website, you can download it. There's instructions and troubleshooting and so on. But of course, you can come tomorrow too. Okay?
Thank